Hello and welcome back to astronomy class. I'm filming this on Thursday, October 20th, after, as you probably know, testing positive for COVID yesterday, although I wasn't feeling all that great Monday and Tuesday wasn't feeling good either. You'll be happy to know I am feeling a little bit better. The fever is gone. I had a sore throat for a few hours and that's pretty much gone now. I wouldn't say I'm completely back to my old healthy self, but we're trending in that direction. So um, hopefully a few more days will kick this thing to the curb. In the meantime, we've got some astronomy to cover. Um, and I'm going to post these videos so that you can keep up with the class material that we're missing on Wednesdays and Fridays class from this week. But before we do that, we should get to today's astronomy picture of the day. So here it is. And this is honestly, normally I don't do astronomy pictures of the day when we're doing asynchronous videos, but this is one I've been waiting for. This is a James Webb Space Telescope image that I have been waiting years for and was most excited for pretty much of any of them. This is the Eagle Nebula from the James Webb Space Telescope. Just so you know, this is a retake of a Hubble image, one of the Hubble's most famous images, called the Pillars of Creation. This is that Hubble image, and these are regions where new stars are being formed as we speak. How do we know this? Because there are lots of other baby stars in the field, and those baby stars, some of them are very massive and have turned on and become extremely luminous and extremely hot and extremely energetic objects that are expelling huge winds into their interstellar medium. And that wind, those winds, carve out the dense material that was used to create the stars in the first place. And that's what we're seeing here. The bright hot stars are all lie above this image, and the winds from those stars are cascading down on these knots of higher density parts of the interstellar medium. And where the density is particularly high, it takes a long time for that wind to erode all of that material away. And so this bright blue material is the places where the material has been eroded away, and you've got some very hot, energetic hydrogen and other kinds of elements, gas in there. And the dark regions are regions where it was so dense that it hasn't had a chance to erode yet. And also those regions that are in the shadow of those very dense regions, right? So you can imagine a wind blowing, and if you have a particularly solid object in there, you can hide behind that wind and not get blown away by that wind because you're in the wind's shadow. And that's sort of what you see here. These fingers are all pointing back towards those source of that wind, those very bright, massive stars up there, and are lying in the shadows of these regions that are the most dense. And we always speculated there was probably star formation going in a lot of these knots, and now we see that directly. That's what this image is. These are the shadows, again, of those dense knots. And now you can see these bright red streaks here are the actual places where gas is collapsing to form new baby stars. It sort of pops out like lightning in these clouds. You can see small little knots here where some star formation's happening pretty much at the end of all of these knots, and then a big event happening at the end of this one. So again, exactly the same region as the Hubble image, but we're seeing it now in the infrared because that's what the James Webb Space Telescope gives us, is infrared light, and we just see a different infrared light can pass much more easily through these clouds, and so we get a much more transparent view of these dark pillars, and we get to see much more what's going on inside of them. And that's what makes this really exciting. So there it is. Spectacular Pillars of Creation, today's astronomy picture of the day. Okay, let's get back to today's review question. It is a question that I asked exactly in this form in the last class that we had on Monday. But enough people got it wrong and were confused by it that I wanted to throw it out again. And obviously there's not going to be any actual top hat credit for this because we're doing this asynchronously, but I wanted to show you what I would have done if we had been meeting on Wednesday in person. So here is the question. Here we have some object with some three-dimensional or two-dimensional space velocity through space. And here's an observer that wants to know what the radial velocity, and we want to know what the radial velocity of this object as seen by this observer will be. We know that this object is moving in 5 kilometers per second, but much of that velocity is perpendicular to the line of sight. And that isn't counted in radial velocity, isn't measured in radial velocity. The radial velocity has no idea whether this object is moving transversely to the line of sight. The only thing that it can measure is the component of that velocity that is along our line of sight. And in this case, that happens to be 3 kilometers per second. So this person observes this object moving towards them at 3 kilometers per second. The radial velocity is 3 kilometers per second towards. And if you remember our sign convention for radial velocity, positive radial velocity is moving away, negative radial velocity is moving towards. So this is 3 kilometers per second, but negative 3 kilometers per second. So the answer would be D. How about if somebody were up here? What if an observer were at the top of the screen, moving, looking down at this object, moving towards it? That would also be a negative radial velocity because this object is moving towards it, but it would be 4 kilometers per second because that's the component of the velocity that's along the line of sight. So this observer up here. An observer over here would see positive 3 kilometers per second. An observer down here would see positive 4 kilometers per second. An observer right here would see positive 5 kilometers per second because the entire velocity would be in the direction of a line of sight. And an observer up here would see negative 5 kilometers per second. Okay, hopefully that helps. Let's do, we left off actually talking about black body radiation and how perfect absorbers and emitters of light, you can't tell what they're made of just by looking at their spectrum if they're a hot solid object. But the thing that does tell you what their spectrum is made of is the temperature. Their spectrum tells you the temperature. And you can tell the temperature based on the peak of that distribution. The shorter the wavelength that peak distribution happens at, the hotter the object is. So we did one example. Let's do another example here, and we can see how this works. So here is the formula we wrote down last time. Lambda max equals 2.9 times 10 to the 6 nanometers kelvins divided by temperature. And the question is, the star Vega emits with a peak wavelength of 290 nanometers. What is its temperature? So let's see if we can solve this problem. Let's see if I can share my whiteboard. There it is. Yay. Okay. So we know that lambda max equals 2.9 times 10 to the 6 nanometers kelvins divided by temperature. But here we're given the wavelength, the peak wavelength, and we're given the temperature. Sorry, we're not given the temperature. We want to find out the temperature. And we're given the peak wavelength. Well, we just need to do some algebra to solve this thing for temperature. So let's go ahead and do this. Let's multiply both sides by T. That will get rid of the temperatures over here. They'll cancel out. We're going to get temperature by itself on top. Now we can divide both sides by lambda max. The lambda max is over here, now cancel out. And we're left with T equals 2.9 times 10 to the 6 nanometers kelvins divided by lambda max. Great. So we know that lambda max is 290. We can just plug that in. Nanometers, 2.9 times 10 to the 6 nanometers kelvins divided by 290 nanometers. And if you take 2.9 million and divide it by 290, what do you get? You get 10,000. And what are the units on this number? Well, we know we've got nanometers, kelvins on top, and we've got nanometers on the bottom. Those nanometers cancel right out, and we're left with kelvins. So this is 10,000 Kelvin. And just to remind you what this looks like, what are we doing here? Well, we're plotting a spectrum which plots the intensity of an object's light, how much light it's giving off as a function of wavelength, and what is that lambda max? It is the peak of the distribution. So it's going to look something like this, and that's lambda max. And in this particular case, that happened at 290 nanometers. A cooler object, if you remember, will be fainter at all wavelengths, and it will peak at a shorter wavelength, a longer wavelength. This is a cooler object. This is a 10,000 Kelvin object. This might be a 5,000 Kelvin object. A cooler object will be fainter at all wavelengths, and its peak will shift towards a longer wavelength. Great. All right, there's one more topic we need to talk about in chapter 5 before we head on to chapter 6. So let's get that out of the way. And that's defining a couple of terms and thinking about how they're related and how we can use them in astronomy. So luminosity is the first term that you need to know. Luminosity is the absolute brightness of an object. How bright I want to say absolute, I mean intrinsic brightness of an object. How luminous that object is how bright it actually is. It's measured in joules per second. So you might say a 60-watt light bulb has a luminosity of 60 watts. What does watt mean? A watt is a joule per second. Remember, joule is our unit of energy. And so our luminosity is a measure of energy per second. How much energy is an object giving off per second? A 60-watt light bulb gives off 60 joules of energy per second. That's an intrinsic brightness. It's how much energy the object is actually emitting into space at any given time. And it is independent of where that object is. The apparent brightness is how bright that object looks to an observer. It is similar to luminosity. You're still measuring energy per second, but now you're measuring it through some aperture, your eyes or a telescope or something like that. So luminosity and apparent brightness are related. Luminosity's intrinsic apparent brightness does depend on how far that object is from us, but they have fundamentally different units, right? Luminosity is joules per second or watts. Apparent brightness is joules per second per square meter. It's a watt per square meter. So you might think of apparent brightness as the amount of starlight reaching through a particular amount of sunlight coming through a particular aperture. Let's say, I don't know, you put some solar cells on your roof, right? They have some particular area. You point them towards the sun. You're going to get the apparent brightness is how much energy is being impinging upon that surface, and that's related to how big the surface is, and also how much energy is actually coming in. Okay, that's the difference between the luminosity and apparent brightness. These two things are, how are they related though? The apparent brightness depends on how far you are away from that object. The further you are away, the lower the apparent brightness is going to seem. And so this is trying to show that visually. In fact, you can sort of figure out how much fainter it's going to look as we get further away. Let's think about that. Let's say you have some light bulb here, and that light bulb's light, like most stars and everything else in the universe, is being emitted isotropically, meaning it's coming out equally in all directions, right? And so obviously, the closer you are to this thing, the brighter it's going to look, but how much? Well, let's imagine 1 second's worth of energy moving away from this thing spherically expanding in a spherically expanding shell, right? How is the size of that shell expanding as it goes away? Well, If you're 1 meter away from that object, you could imagine all of the light that's contained within this 1 unit cell, right? And that's a particular amount of energy, right? A particular amount of energy that is contained within this 1 square unit cell. Doesn't even matter. Doesn't even matter what the units are. If we go twice as far away, that same amount of energy is now spread over an area that's 4 times as large, right? Because we have taken that whole surface area and we've expanded it, and we're spreading that energy out over a much larger shell now. If you double the distance, in fact, you have increased the total area of this sphere by a factor of 4. And if you triple it, you've increased it by a factor of 9, because the area of a sphere is 4 pi times the radius of that sphere squared. And so if you double the radius, you're increasing the area by a factor of 2 squared, or 4. You're tripling it, you're increasing it by the area by a factor of 3 squared, or 9. And so you can see any one patch of this is getting spread over a larger and larger area as you get further and further away, and therefore the apparent brightness is going down by that same amount, right? You're taking the same amount of energy here and spreading it over 4 units. Therefore, the brightness must be 1/4 as much in each one of these other square units that we had before. And when we get 3 times further away, the same thing. That same energy is now spread over 9 units. And we get each of these 9 units having 1/9 the brightness, energy per second per unit area, that it did when we were at 1 meter away. And this is the inverse square law of light. So the area of a sphere goes as 4 pi r squared. So the brightness must be proportional to 1 over r squared. You increase the distance by a factor of 2. You decrease the brightness, the apparent brightness, by a factor of 4. Here is the actual equation that we might use to calculate between brightness and luminosity, but it's really it's the luminosity. The brightness is the luminosity divided by the surface area of a sphere whose radius is the distance from that object. And hopefully that's obvious to see here, right? If this lamp is emitting 60 watts of energy per second, then if you go, you want to know what the brightness of that is, you just have to spread that 60 watts over an area that is a shell completely surrounding that light bulb. And so you'll get only a fraction of that energy passing through each square meter as you move further and further away from it. So it's just the luminosity, the actual amount of energy being emitted, divided by how much we have to spread it over, what the area we have to spread it over for a sphere of that radius. And so this is a good way to determine how bright an object will appear if it's moving further away from you, say. And in fact, it's very difficult in astronomy. We're not going to talk about this a lot in the solar system because it's very easy to get distances of the solar system from other ways. But for objects outside the solar system, distances are really hard to get. And one of the ways to do it is by this technique. You can always measure the brightness of something. If you happen to know something about that object that tells you what its luminosity is, you can actually turn this around and solve for the distance. And that's the standard candle way of measuring distances to things. If you know the luminosity of an object and you can measure its brightness, you get its distance out basically. And so obviously you can turn this around too, the luminosity of an object. If you know the brightness and the distance, you can get the luminosity just by multiplying that by the brightness by the area of that shell, 4 pi times the distance squared. Okay, let's take this equation out for a trial run and see if we can use it to calculate something useful. So the brightness of the sun at Earth is about 1,300 watts per square meter. This is an important number. This is called the solar constant. This is, again, if you put your solar panel on the roof and you've got a full square meter of it, say, you're going to be the maximum amount of energy that you could possibly get from the sun would be 1,300 watts per square meter, because that's how much energy is actually reaching us every second from the sun, 1,300 watts in every square meter. So, of course, you don't actually get this on almost any solar panels, because the efficiency is nowhere near one. In fact, the efficiency of most solar panels is still in the 5 to 10% range, even for the best of them. So you're never going to get anywhere close to this. But the bigger array you have, the more sunlight you can catch, and the more energy you can actually capture and generate. But the question is, what is the brightness at Pluto? The semi-major axis of Pluto's orbit is 40 astronomical units. So what is the brightness that we would see at Pluto? So let's take a look. So we know that the brightness of an object equals its luminosity divided by 4 pi times the distance to that object squared, right? And this is what we're interested in. We want to know how the brightness changes from Earth as opposed to the brightness change, what it looks like on Pluto. So we can say the brightness of Earth is equal to the luminosity. This is of the sun. I'll put a little s here. And this is the distance between the sun and the Earth. This is really the semi-major axis of the Earth's orbit in some level, because that's the average distance between the Earth and the sun. But what's the brightness at Pluto? Well, the brightness at Pluto is also the luminosity of the sun divided by 4 pi times the semi-major axis of Pluto's orbits squared, right? And what we want to know is, well, we want to know the brightness at Pluto, but we can use this and set it up as a ratio. And if we want to know a ratio, we can get rid of some of these things. For instance, we don't need to know what the luminosity of the sun is. Why? Because we're really just interested in the ratio of these two brightnesses, right? So let's do this. If I were to take BE and divide it by BP, which is taking a ratio, what is that going to be? Well, I know the brightness of the Earth is the luminosity of the sun divided by 4 pi times the semi-major axis of the Earth squared. I know that the brightness on Pluto is the luminosity of the sun divided by 4 pi times a Pluto squared. The power of taking ratios is a lot of this stuff just goes away, right? The luminosity of the sun is the same on top and bottom. I can cancel those out. The 4 pi, I've got the same on top and bottom. I can get rid of those. Those are cancelable. So what do I have? I have 1 over AE squared divided by 1 over AP squared. Well, that's weird. But I can, this is 1 over AE squared. And if I have, on this one, if I have a denominator in the denominator, that can actually move up to the numerator. And this is, in fact, AP squared over AE squared. And I don't even have to square them before I take that ratio. I can take the ratio and then square them. So this is really AP divided by AE quantity squared. Well, guess what? I know what AP is, and I know what AE is. AE is the semi-major axis of the Earth's orbit, which in astronomical units is defined to be 1. And I know from the problem statement that AP is 40, right? So this is BE over BP. The brightness ratio between Earth to Pluto is 1 as far as 40 over 1 quantity squared. Because I know this is 40 AU and this is 1 AU, and those are going to cancel out. And I've got 40 squared. 40 squared is a big number. 40 times 40 is 1,600. So the brightness of the sun, as seen from the Earth, is 1,600 times greater than it is at Pluto. And since we know what the brightness of the Earth is, we can solve this for the brightness of Pluto now. Let's multiply both sides by BP and divide both sides by 1,600. The BP's cancel out over here. The 1,600s cancel out here. And we get BP on one side, and we get BE on the other, divided by 1,600. And we know what the brightness is of the Earth. It's 1,300 watts per square meter divided by 1,600. That's a little bit less than 1 watt per square meter. 0.81 watts per square meter. So if you want to know why those objects in the outer part of the solar system are little frozen ice balls, this is why. The energy that they receive from the sun goes way down as you get further and further out in the solar system. We're getting 1,300 watts per square meter of energy. Pluto's getting less than 1 watt per square meter of energy. All right. I'll come back in the next video. We'll start chapter 6, telescopes. See you there.